All right, so let's do polar coordinates and integration. So before I introduce integration in polar coordinates, I have to extend the usual U substitution to two dimensions. So think about U substitution in one-dimensional context. So if f was a function of x, and now you're trying to define u as a function of x, and you want to go from u f dx to f du, the way you do this is by writing it as f dx du times du. That's u substitution, right? So as an example, I mean, since this may look kind of different from the way you looked at u substitution. So let's see. Suppose you're integrating, say, 0 to 2 of x to the, let's see, x times x squared plus 1 to the third dx. And then the way you do the u substitution is you set u equals to x squared plus 1. And then you do du equals to 2x dx. If you differentiate this as 2x and you multiply by dx, and you're told to divide the 2x and rewrite dx like this. Now, so that's the way you've been learning u substitution until now. But trying to view u substitution this way means the following. Instead of thinking of u as a function of x, think about x as a function of u. So try to solve this for x. So you get u minus 1 equal to x squared. And you solve for x, so x is square root of u minus 1. And then you say dx is equal to derivative of this by x, no, by u du. And then if the derivative of this is 1 over 2 times square root of u minus 1 du, just by using the chain rule, you can figure out that if you differentiate this, you get that. Right? And compare these two. One says dx is this times du, other says dx equal to this. And if you look at this and this, it's the same thing, because what is x? X is same as square root of u minus 1, right? So they're exactly the same thing. So whether you view u substitution this way is or that way, it's equivalent. Okay. I don't mean to suggest that you should be doing u substitution this way. No, that's not what I'm saying. I'm just saying that the prior u substitution that you know so far can be written in this form. Now, the upside to this type of u substitution is that it kind of makes sense, because if you just cancel du out, you come back to the original one, right? It just makes sense, right? And in this case, just to demonstrate how this thing works, see this function as written as a function of u, since x is this thing, you can write as x can be replaced by that, and this can be replaced, since u is x squared plus 1, you can replace this by u cubed And by the way, when x is 0, u is 1. If you plug in 2 into x, 2 squared is 4, 4 plus 1 is 5, so instead of 2, you have to put 5. And then you multiply, instead of this dx, you write down 1 over 2 radical u minus 1 du. So it's 1 over 2 radical u minus 1 du. And they cancel, and you compute this. Let's see, what's the answer? This is 1/8 of u to the third, u to the fourth, and you're doing 5 minus 1. 5 to the fourth part is 625 minus 1, 624 divided by 8. What's that? 7, 44. Oh, okay. 64, okay, 78. Right. So that's what you get, okay? And if you do it the traditional way of doing the u substitution, you'll find that the integral you get is exactly the same as this one. Okay? So I'm just pointing out that writing down u substitution this way is exactly the same as how you know it. Okay? Now, the reason I'm writing down the u substitution in a strange way is because when it comes to double integrals, this way of viewing it makes more sense. So, so think about the following case. Let's say you're trying to integrate a function now by dx dy. And then you have some kind of function u and v as a function of x and y. I don't even want to think about what exactly they are. So it's some mixes of x and y, like 2x plus 3y, whatever. And my goal is to actually rewrite this integral. Actually, it's a double integral. My goal is to rewrite this integral as a double integral in terms of u and v. And the formula that you have to use is very similar to that. It's like f times round round xy over round uv du dv. And this thing over here means the following. Just like how instead of viewing u as a function of x, you had to solve to get x as a function of u. It's the same story. Even though I'm kind of introducing u and v, the way this thing is calculated is like the following. First, you have to solve for x and y, so you have to write down x and y as function of u and v. And once you have it that way, then this thing is actually sorry, I think a lot of times people write this. Okay. So this thing is actually the determinant of all possible derivatives, all possible partial derivatives. So since x and y are now functions of u and v, you can take x and differentiate by u. You can take x and differentiate by v. And then you can take y and differentiate by u, and you can take y and differentiate by v. So that's the generalization of this into two-dimensional integration. Now, it would be nice if I had the time to explain why determinant is used, but that would require some more mathematical investigation into transformations and planes, and it's a lot more complicated. So at this point, if you can just see the similarities between the one-dimensional one and a two-dimensional one, then that's enough right there. And there's a name for this thing. This is called the Jacobian of the transformation. So if you think about the function, some kind of transformation that sends u and v into x and y, this thing is called Jacobian of the transformation. So that's the name, but all I want to say is that's the name. This is called a Jacobian. And for our purposes, we don't really need to know this symbol. We just have to know how to calculate this. All right. Now we come back to integration and polar coordinates. And here's what we aim to do. We want to integrate some function that we used to differentiate in terms of dx and dy. And now we want to rewrite this as an integral of this same function in terms of dr and d theta, because in polar coordinates, those are the numbers that describe the points, right? Now the question is, according to this formula for change of variables in 2 dimensions, what is this quantity? That's our question. If I'm doing some change of variables, there must be something there, and what is this quantity? So I want to figure out what this is. And according to that prescription there, what I need is I need to explain x as a function of r and theta and y as a function of r and theta. Do you know such a formula? X is
r cosine
theta. And y is
r
r sine theta. Okay. And now let's compute that determinant. So according to that prescription, what I need is I have to differentiate x by r, I have to differentiate x by theta, I have to differentiate y by r, I have to differentiate y by theta. Which is, let's see, if I differentiate this by r, what do I get? Cosine theta. And if I differentiate this by theta, I get negative r sine theta, right? Because if you differentiate cosine, that's negative sine. If I differentiate this by r, you get sine theta. If I differentiate this by by theta, I get r cosine. And this thing here means it's the determinant, so let's find the determinant. Like this. So this times this minus this times that. So cosine times r cosine theta, that's r cosine squared theta. And then minus, this times this is negative r sine squared theta. Minus minus is plus, and since they both have r, I can factor the r out, which gives you cosine squared theta plus sine squared theta, which is 1. So you get r. Therefore, what goes in here? R. R goes in. Okay. So the thing that we just proved is the following fact, that r dA, which is written as dx dy, or dy dx in rectangular coordinates, in polar coordinates requires r times dr times d theta. You have this extra r. Okay. Now, when you see this for the first time, it's kind of hard to accept. So just showing you one calculation and saying this is it is probably not enough for you to be convinced that that's what you need. So let me add some more perspective on why this is reasonable. Okay. The first thing I want to say is it makes sense if you just look at the units. So what's the unit for area? In MKS units, it's square meters, right? If we are doing physics and we're talking about area, we have to use square meters, right? What's the unit for dx? Dx is a small increment in the x direction, so it's meters. And what's the unit for dy? Meters. So they do match, right? Meters times meters is meters squared. So they have both the same unit. Okay. Suppose you didn't have this, then you see the problem immediately. See, dr is meters. What's the unit for angles? Degrees or radians? We're using radians because we're using it for lengths. And by the way, radians actually in MKS units has no dimension. It's dimensionless quantity. Angles are dimensionless. That's because when you use radians, you often use this formula called SOR. Length of an arc is the radius times the angle measured in radians. And because this is meters and that's meters, this has to be dimensionless. If that has another dimension, that times that has to be the new dimension of this. So because of this, angles are considered to be dimensionless in the MKS units when you're doing physics. Okay? So you should really think of this as dimensionless. So just say 1. So if we didn't have this r, the dimension of this quantity will be just meters. Is that good? No, that doesn't match with the area. So now think about the unit for r. R is the length, right? So it has a unit of meters. So therefore, I have meter square, meter square, meter square. Everything matches, and it makes sense. Okay. So that's one way to kind of convince yourself that you need something more than just this. So that's one way to see it. And then here's another way to think about this quantity. All right. So I shouldn't have erased this, but because that's really important. So if you have a very small increment in the angle, and let's say this length is r, right? Then think about what this length is. So using the SOR, that arc length is the radius times the central angle, radius times central angle times the central angle times the radius. Then, because in this context, the central angle is denoted as d theta, not theta. So it's d theta times r, and therefore this length is r times d theta. That's this length. So when you see this, really what's happening is r times d theta is this length here. And then what is dr? Dr is a very small increment in the r direction, so that's dr. So if you multiply this with this, you get this area, because because this angle is so small, although this is curved, if this is very, very small, it's almost like a straight line. So when you calculate this area, it's just dr times r d theta. And definitely this thing that you get by multiplying all this is a very, very small piece of the area, right? Okay. So that's why this has the meaning of dA. It's a very small piece of area. So that's another way to understand this r d or d theta. Okay. But these just looking at the units is a very rough way of seeing it. This is slightly better, but not completely satisfactory. The best way to see that you really need this r dr d theta is by using this Jacobian. But this one I really didn't provide you the full picture, because to explain why the Jacobian works, it requires treatment about transformations of planes. Okay, so just to demonstrate that this really works, I guess the best way to show it is by showing a very, very trivial example and show that it does work. Okay, so here's a trivial example. Think about the unit circle. Now, what's the equation of this unit circle in polar coordinates?
X squared plus y
But that's rectangular. X squared plus y squared equals to 1. That's rectangular.
R cosine squared.
Yeah, but it's much simpler than that. What's the equation of this unit circle? Huh?
360. Sine theta, sine squared plus cosine theta.
R equals to 1. That's it. If you collect all the points that where the radius is 1, you get all the points of the unit circle, right? Okay. Yeah. R equals to 1. Okay. So that's the equation for the circle. Now let's think about integrating over this circle 1 dA. Okay. Now I explained before that such an integral means area, the volume under the curve, volume under the surface. So you really have to think about this function z equal to 1, which is a plane of height 1, over this domain. Okay. But see, if you have something that has the same height, the volume of this object is just same as the base area times the height, right? That's how you get the volume of a column, right? And especially when this height is 1, what's the volume? Volume is just same as 1 times the base area. So you end up with just the area of the base area if you're integrating 1. Okay. So by the way, this is something that we're going to use a lot. We're going to say that if you want the area of a domain, just integrate 1 over that domain, because that's going to give you the base area. Okay. So what's the answer for this if we computed this? See, what's the base area? I'm talking about this one. Pi. Pi. It should be pi, right? See, the formula for area is pi r squared. That's for the circle, but the radius here is 1, so this is pi times 1 squared. So that's just pi. It has to be pi. Okay. So this is a very, very trivial example, which I want to use our knowledge to it because it's so straightforward. Okay? So if our calculation does lead to the same answer, then we can fully trust this. Okay? So let's see. If I have, so according to our prescription, we have to do 1 rdrd theta. 1 rdrd theta. And then I have to describe this domain as r and theta. So for radius, any point in here has r value between 0 to 1, right? The maximum r value could be 1 when it's at the edge of the circle. How about the angle? Angle varies from where to where?
0 to
0 to 2 pi. So you can say r goes from 0 to 1, whereas theta goes from 0 to 2 pi. Let's compute this. Let's see what it gives us. So if you integrate this, this is 1/2 r squared. And we're plugging in 0 and 1. And when you plug in 1, that's 1/2. When you plug in 0, it's 0. So now you have to integrate 1/2 d theta from 0 to 2 pi, which is 1/2 theta. And now I plug in 2 pi and 0. What's that? If I plug in 2 pi divided by 2 is pi, and plug in 0, 0, pi minus 0 is pi. So done. Right? So it did give us the correct answer. So that should be like the fourth argument for that this is the right one.